My name is Shiang Yu Lee. I have a PhD degree in mechanical and aerospace engineering from a very long time ago. I have been retired for 20 years, but when I was working for the Boeing company, I was never worked on aerodynamics. After I retired, I felt the urge to study aerodynamics, and since then, over the 20 years, I have created several papers and presented them to AIAA conference, and but they were not very satisfactory, and so I kind of rework on this one to try to present to this community. And I'm very happy that this is a applied math and science conference, because my work does have to do with mathematics a little bit. I'm proud to say that I have even created some equations out of my research here. So we'll see what I can do. But before I present the paper itself, I would like to give some introduction to the field of aerodynamics to the audience, as I believe most of you are not very familiar with this curricula. Anyway, there are very many misunderstandings about aerodynamics or how the airplane fly. But I think this picture by NASA shows it all. This is showing a crop duster airplane flying by a smoke generator. The smoke was red smoke, and when it flies by, as you can see, there's a huge vortex being created by the airplane. And this is really how the airplane flies. But if you go on GPT to find the answer, they'll probably not give you a good answer like this. So before I go into my paper, I will give a very brief historical review of the aerodynamics subject area, and my critiques of the state of art of this area. Okay, now speaking of aerodynamics, we deal with lift and drag, and more than 200 years ago, Newton, I think, was one of the first person that really produced an idea of how aerodynamic force works. He only dealt with the drag force. However, he did get the right idea that for a flat plate, the drag force is given by this equation that he wrote down. So Fd, the drag, is proportional to sine alpha squared. And to write out the equation more fully, it can be written as Fd times k rho a v squared sine square alpha. And sometimes in our field we call this the sine square law, but this is really a right answer to the drag problem of a flat plate. So we may say that this is really the beginning of aerodynamics. Now, as I was saying earlier, that the lift is really created by vortex, and here we show that in 1852, Magnus had the idea, or he has the observation that if you are playing a ball like a baseball, and if you spin it, then if it will fly in a strange way, and he realized that it will create a force when the ball or a cylinder is flowing, is rotating, and this is what we call the Magnus effect, and it was formalized by Magnus in 1852. Even today, people are still marveled by this, and there are commercial ships trying to use this Magnus effect to create lift like a sail on a sailboat. Now, since a cylinder or a ball, when it's rotating, it'll create a force perpendicular to the direction of flight. And that's the amazing part about it. And this theoretical work was eventually done by Kuta and Joukowsky in the early 1900s, okay, the turn of the century, for 20th century. They independently discovered this fact, but today we usually bring them their names together to say it's the Kuta-Joukowsky theory. I'm not American, so I read it as Kuta-Joukowsky, but the Americans would read it as Kata-Joukowsky. Since I guess most of us are not Americans here, we can laugh at them for pronouncing it the wrong way. Anyway, I think Kuta formalized the theory that circulation will create lift, but Joukowsky is the one that applied the transformation of a circle into a airfoil shape, and then created the modern airfoil. And this became the Kuta-Joukowsky theory of flight. And we have a beautiful equation. Lift is equal to rho times v times the integration of the circulation. Circulation is, of course, is the other form of vortex we're talking about here. Circulation is the vertical flow around an object. Okay. Now the Kuta contribution to this theory is saying that in order to have the lift on the wing, you must have the flow at the tip of the tail to flow out smoothly, and that's the criteria of how to determine the circulation strength. Okay, so this will be the fundamental theory of aerodynamics, but I will also say that this is the only real theory of aerodynamics. Ever since that time, we haven't had a real theory. And that's why I'm here trying to say that we have work to do. So here again, I put this theory in terms of the flight of airplane to give you a better picture of how what's the importance of this theory. Now that was done around 1900, okay? But we haven't had much progress after that, not until the 1920s that we have Pronto, the scientist, well-known scientist from Germany, to came up with the lifting line theory, where he has managed to describe the vortices or circulations on the wing is like a system of vortices, and they change, and when they change in the magnitude, then they leave a trail of trailing vortices behind it. And what he had found out from this what we can call the lifting line elliptic distribution theory is that with this theory you can calculate the relationship between circulation, lift and lift coefficient and drag coefficient. This is the famous drag due to lift theory, or the drag polar of Pronto. And that is the basic theory of modern airplane aerodynamics. But I have to say that this equation is not quite right, okay? If you look at the test result using this formula, they don't really match, okay? And after that theory, I think the only contribution in the field of aerodynamics was the what's called the leading edge suction analogy. It was created by Paul Hammes of NASA in the 1960s. He found a way to approximate the aerodynamics, and he created some equations, but he really didn't have a closed form solution for the equations, but he uses approximation solutions to guide his results. But he was able to say that his results matched the test of delta wings very accurately. I challenge his claim, but that's not within the scope of this talk, so that'll be probably in another paper later on. But anyhow, aerodynamics throughout the years has tried to do a lot of things, but cannot really create any real mathematical theory to it. And most of the companies or most of the scholars are now using computer simulation to do the job. And there's no new science since, you may say, 1960 or 1920 even. There's really no new science in there, okay? So yesterday when I was preparing for this presentation, I saw this picture in my computer, which says no science innovations since the 1920s, which matches exactly what I was trying to say here. Okay, so with that, I'll switch over to my real presentation. Do you see it here on the screen, or do I need to excuse me, somebody can tell me if you see the presentation?
Yep, we can see the presentation.
Okay, great. Then I'll start the video on this also. Greetings, my name is Shiang Yu Lee, and I would like to present to you my research on the vortex.
Oh, it's the wrong one.
It is very well known from
You
Earth.
need to unshare and share.
Okay, yeah, sorry. I don't see the share voice. Sorry, my screen is playing a trick with me. And three distinct elements. In this research, we present three distinct elements of aerodynamic forces: the potential lift, the crossflow separation vortex, normal force, and the nonlinear Newtonian drag or pressure drag. Pronto showed us 90 years ago experimentally of what happens when the wing starts to move in the fluid. Two vortices forms quickly. The trailing edge one drifts into the wake quickly, and the front end vortex wraps around the entire wing to become the bound vortex, providing lift to the wing. And this is the kickoff point of our research. This is how we model mathematically what happens when the plate starts to move. Two sets of vortices forming at each end of the plate. Of course, these vortices cannot stay forever, but they determine what happens afterwards. When the rectangular plate starts in motion, the reflective flow or circulations starts in all directions, but in a very well organized manner. It's like a water stream falling on the ground. It splashes in all directions. We suggest that the rectangular wing can be divided into four separate zones. Zone 1 in the front section is where the bound vortices is generated. Zone 2 on the side, the vortices cannot stay on the wing. That's where the wingtip vortices are formed. And zone 3, the back section, is where the vortices will drift into the wake and forming the starting vortex. The zones are defined by the bisect lines and the center line. Now that the geometry of the flow can be defined, if we also know the vortex strength, then we can determine the complete solution. Similar to the electromagnetic theory, a circular plate circulation will take a toroidal shape. If we want to maintain constant speed through the return area, the return area dimension must be changed. We determined that the finite plate has reduced circulation capability, and the maximum circulation is defined as a function of aspect ratio. The circulation strength and the lifting capability is further affected by the orientation of the circulation. With the circulation strength and the flow orientations determined, we can now calculate the potential lift of the square plate and the narrower plate. As we find out that the result agrees with slender wing theory completely. However, we have arrived at the conclusion from a totally different perspective. Now, for the wider wing, we approximate the midsection of the circulation distribution by a parabola. And this is the result of the potential lift. Comparing to the experiments, we see that the values are a little higher than experiment data, but not as much as frontal lifting line theory. Milne-Thompson introduced a Vortex Impulse Theory in the 1940s, but the theory has never received any attention. The theory states that if you have a ring vortex, it can be considered to be the result of an impulse applied to the ring area. Now, if the ring grows with time, then the force applied to the fluid can be calculated with computing the growth of the area. Now, if we have a rectangular wing, then the vortex ring area is simply the wake defined by the trailing vortices and the starting vortex. This theory then allows us to calculate the force imparted on the fluid when the wing is shedding the crossflow vortex. This vortex force is normal to the wing because the vortex is created by the wing and therefore it's normal to the wing as well. We assume the shedding vortex reached the maximum at the center core location. Here's the resulting vortex normal force coefficient. Notice that it's a linear function of sine alpha. We also introduced a set of empirical functions for the pressure drag or nonlinear drag force. Before applying the equations, we checked against the experimental data again and found out that for narrow wings, all the forces are normal to the wing, so there should be no potential force in these cases. In light of that, we truncated the potential lift and limited it to the mid-span regions. The truncated potential lift is added to the separation vortex normal force to build up the total lift. Here's how we construct the overall lift and drag from the three distinct force elements and also the applicability of each one of the elements. In comparing to the Lamar test data, we see that both lift and drag fits the experimental data perfectly. We can match the winter test data as well. For the square plate, it not only fits the data, but also the curvature all the way up to stalling. The wider plate cases are equally remarkable. Finally, we made a comparison to the Horner idea of a second lift or nonlinear lift and found out that we can emulate his interpretation of the data completely. In conclusion, we have introduced three sets of new simple algebraic equations for the aerodynamic forces. and their applicability are assessed and asserted, and the results match experiments perfectly. But most importantly, we have introduced the idea of crossflow separation vortex linear normal force into the way to evaluate them. And we also revived the vortex impulse theory and to make it available for the academic community. Okay, I cannot see myself. Let me see. Okay, all right. That is my presentation. If there's any question, I'm happy to respond. Thank you.